everyone. My name is Lindsay Shuck. Thank you for joining the Family Office Network's webinar series featuring Ecellix. Presenting today will be Jerry Schwartz, CEO and Chairman, a past executive for Microsoft Corporation, and Dr. Jeff Dean, founder of Bill Gates Academic Ventures Innovation Labs and a graduate of MIT. At the end of the presentation today, we will have time for Q&A. Please send over any questions throughout the presentation using your questions drop-down option so Jerry and Jeff can answer them accordingly.
Good morning, everybody. As Lindsay introduced, I'm Jerry Schwartz. I'm CEO and co-founder of Ecellix. We're a Seattle-based company that is commercializing technology developed here in the state of Washington at Washington State University and now continuing development at University of Washington. We are in a really interesting time, what I call an area of disruptive change. And what this amounts to is that things are changing really rapidly. If you think about it, 1879, the incandescent light bulb came out, and it's really only been in the last 20 years that we've made improvements in terms of lighting capacity. Portable data storage, 1981, 360K floppy disk. We're now at 2 terabytes on a jump drive. And recently it's been announced that the biggest revolution in cars since the Model T is the electric vehicle. So we're really moving into some new eras that are really fundamentally changing things. These are very disruptive markets and huge market opportunities and huge investment opportunities. And so I would invite you to consider what I would call the cordless future, or the battery age. The battery age is really interesting in that it touches everything. As we'll talk about, it's cars, it's tools and devices, it's home storage, it's grid storage. It's really going to touch everything in your world, and it's going to be worth billions of dollars. The current market approach is 2024. It's a $100 billion market for lithium-ion batteries, growing at 18% annually, projected to be $200 billion by 2030. So growing rapidly, and our space in that's actually pretty substantial. So for the next part of our presentation, I'm going to hand off to Dr. Dean. And he could share a little bit about what we're doing, our eCell technology, and then I'll come back and share some more things about our business model. Dr. Dean.
Hi, I'm Jeff. I'd like to talk to you a little bit about batteries as a whole and about what we're doing here at Ecellix. Ever since about 1991, when lithium-ion batteries were first introduced, they've been increasing at a very, very small but incremental rate every year, increasing the amount of capacity, largely due to manufacturing advances of the batteries and to advances in cathodes. A battery has 4 key components. It has an anode, which is the negative terminal on the battery, a cathode, which is the positive terminal on the battery. It has a separator, which is a fabric-like material which keeps the two apart, and it has an electrolyte, which allows ions to move from one side of the battery to the other. Ever since 1991, the advances have been all in the cathode, or the positive side of the battery, and we've been using the same material, carbon or graphite, since that point in time. As you can see, even in 1991, researchers were able to actually look at this and say that there were better things to do than graphite. Graphite had a capacity of around 375 milliamp hours per gram. And when we went up to silicon, we could actually get over 10 times as much lithium stored in the silicon as we could in that carbon. So they've known about this for a long time, and there's been a huge amount of money invested in trying to move from a graphite-based battery to a silicon-based battery. The problem has been that as we move to that new technology, as I put lithium into the silicon, it expands 340% in volume. When that happens, the silicon metal, it expands and contracts, and it starts to crack and break apart when it's fully charged. To date, that's stopped people from being able to introduce silicon-based batteries. So we're going to introduce and talk to you a little bit today about eCell, our revolutionary battery technology. It's based on a silicon anode that is proprietary. It's a swell-tolerant material, meaning that as I drive lithium into it and lithium out of it, as I'm charging and discharging my battery, it swells and then relaxes, but it doesn't crack. This is based on a series of advances that came from research at universities, and it's a fairly fairly important increase to this. As I said before, batteries are increasing at 1 to 2% per year. This one technology may enable us to increase the 30 to 50% leap in energy stored in a battery. It is akin to when we moved from nickel metal hydride batteries to lithium ion batteries in the early 1990s. So how do we do this? Well, as I said before, the challenge that we have is as we're driving lithium into silicon, it expands. Then when we take the lithium out of silicon, it contracts. As that happens, that material will crack. It also, as it cracks, it's exposing more surface area of the silicon, which leads to a series of reactions that we don't like to have in the battery. So we have these two problems. One is that we're expanding and contracting, causing cracking. And as we crack, we're exposing more surface area of the battery, which leads to reactions in the battery, which actually hurt the battery and cause it not to last very long. So we're looking for technologies that enable us to build batteries that can expand and contract, and at the same time manage the surface area so we don't get harmful internal reactions. Our novel material approaches this in a very clever way. We start off with a very simple metallurgical grade silicon, very inexpensive, very easy to handle. We alloy it with a metal. We then subtract that metal, and what we're left with is something that looks like Swiss cheese. As you can see here in these three photographs, the left-hand photograph, we're starting off with silicon particles. We alloy it with a metal. In the middle photograph, these are scanning electron micrographs. And in the right side picture, we actually have what's left of our material. Now that structure on the right is very important. What it allows is very, very small particle sizes that can expand and contract without breaking. And at the same time, those particles are coated with carbon. And that carbon prevents the material from reacting with the electrolyte. It prevents those surface reactions which harm a battery. By making this all in a single process, we're able to use very low quality, inexpensive, off-the-shelf components, and we're able to drive to a material that simply works. Go to the next slide.
Yes, please.
Thank you, Jerry. As we can show on our material, historically, graphite was operating at about 375 milliamp hours per gram, meaning that's how much energy it could store per unit of mass in the battery, or for how much energy I could store in a single cell. When we move to a silicon-based cell, we can see the jump here shown by this arrow, where we're jumping from a little over 350, or just about 350, to over 1800 milliamp hours per gram when we're going to silicon. And on the other side, when we run this battery over and over and over again, we find that we're holding our capacity, it's not breaking apart and failing. And so after almost 600 cycles of a battery, we're still maintaining 80% of the capacity of that battery. This is a very important finding and something that is not common in batteries. So what's happened historically is we've been looking at technologies that have driven primary structures. People have been working on these technologies for the last 20 years, and they've gone through a whole litany of different types of technologies, all based on taking small particles and then building larger particles that don't have those kinds of surface chemical reactions. Billions of dollars have gone into research trying to solve this problem. They've gone from coated silicon nanoparticles, very small nanotechnology, silicon graphite composites, and going to alloys of metals, mesocarbon microbeads, thin films, carbon nanotubes, double wall nanotubes, silicon nanowires. What's emerged in the last about 5 years is a new class of material based on a concept called porous silicon. And it's led to something called porous silicon carbon composites. eCell, Ecellix's novel material, is a new take on this called microporous silicon carbon composites, where others have tried to approach this from building porous silicon carbon composites, starting off with nanoparticles that are very small, very expensive, and hard to handle. We're building these materials using metallurgical grade silicon on the micron scale. And it makes this simple to manufacture, easy to scale, and high performing. Where this leaves us is as we're looking at what we've done versus others. You can see in the right-hand column, there are at least a dozen companies in the United States who've been trying to do this dating back about 12 or 13 years. They all emerged from university research, and they all emerged from sort of the leading and prevailing research at the time. Most of them are predicated on the idea of nanotechnology, using small nanomaterials that solved the problem of this cracking. When the particles got small enough, when they expanded and they contract, they didn't break. So silicon was able to hold more lithium, and they were able to make it so that the silicon was not cracking and breaking apart. But as they built it, they had a huge problem with creating surface area. They had a problem with all the other dynamics happening inside of the battery. And in the end, what it leads up to is a material that is very expensive. Instead, by starting off with micron scale materials and synthesizing subtractively, starting from a top-down synthesis approach, we're able to actually produce materials that have a high lithium capacity, withstand cracking, and start implicitly from the perspective of being low cost and having these other problems solved. So as we look at this, it's not just us saying this. This comes from one of the most prominent review articles in the last couple of years. This group looked at all the different technologies that had been done in silicon anodes over the last 20 years. And they came to the conclusion that says, although nano-sized materials can achieve stable cycling performance by addressing pulverization, so these other materials are able to start off with small particles and not crack, and then combine those particles into elegant structural designs to try to counter this chemical coating problem or surface reactions problem. They lead to other problems in the battery. And these other problems in the end lead to a high cost. So we're really excited about the way we're approaching this because we think we're coming at this from the opposite direction, and it's leading to something which starts off at a low cost, a high manufacturability. It makes the battery a whole lot more approachable. We've put together a team of experts to go approach this technology. On our team in our laboratory at University of Washington, we've got 3 people very skilled in batteries. We also have a team over at Washington State University where the original discoverers of the technology are working with us on advancing. We've put together a technical advisory board, including Brian Holloway, who's the Vice President of Deep Science Fund and Intellectual Ventures and formerly of DARPA. George Crabtree, who's sort of one of the godfathers of battery technology at Argonne National Laboratories, and other experts like Dr. Parikh, who is a silicon anode technology specialist. You can see down at the bottom, we're actively working in the laboratory. We were working today in the group. Our group is there synthesizing batteries today as we speak. We put together a consortium of people, different companies that are helping us to work on this technology, from Pacific Northwest National Labs, Polaris Battery Laboratories in Beaverton, Oregon, Croda and Cabot, 2 large material science companies, Washington State University, and Pyrotech, which is a company which specializes in scaling the synthesis, scaling manufacturing of materials of this type.
So we talked about this being a really large market. It's actually a concentrated market, so there's several key players that it'll be important for us to be successful to align with. On the left, you'll see kind of in terms of battery manufacturing, the primary players, and it's dominated by 3 key players: LG Chem and Samsung out of Korea, Panasonic out of Japan, correspond to about 60% of the overall global market for lithium-ion batteries. Then a variety of players, a lot of them in China, make up the balance. You'll notice on there, we have those 3 named in NDA next to that. And what that's a reference in is that we have NDA-based disclosure and relationships with these 3 companies and ongoing dialogue. Ultimately, the opportunity is they would be 3 of the potential acquirers for this technology in the longer term. The more interesting player actually is Hitachi Chem. when you look at these three players that are the dominant in the marketplace, they secure all their current graphite anode materials from Hitachi Chem. Hitachi Chem has just gone through a merger with Showa Denka in Japan. They're now a $20 billion company, and they control, between their share and the share of Showa Denka, about 60% of the global market for anode materials. So everybody is turning to them for these materials. They've been courting us really heavy for a couple of years. I've had several visits from their chief technology officer. His last dialogue is, we'll either license materials for you or we'll buy your company. We'd be very happy with that outcome, and that's something that is not a long horizon thing. It could actually be in the next couple of years. Also, another approach that we do is we're dealing with the actual end consumers. So rather than just putting it in the battery manufacturers, whether to adopt our technology or not, and competing with their own research efforts, we've gone to a number of the major consumers: BMW, Daimler, PACCAR, which is the #2 in the world for large commercial trucks, Lockheed Martin, where we mentioned earlier Dr. Holloway was the chief technology officer for Lockheed Martin's Advanced Technology Division until 2 years ago when he joined us, and Honeywell and a couple of others of that stature. So these are all people that are actively engaged in partnering with us to do the appropriate solutions for their particular needs. You'll see on the market that there's really 4 major market sectors for this technology to apply. So this is really along the lines of a platform. We didn't really talk about it, but the flexibility of this solution is that we can modify what we deliver in the materials in such a way that it has optimal performance for industrial applications, which can be things like tools, still power saws, lawnmowers, all of the types of things that we're making a rapid evolution over to a cordless society. Automotive is the most aggressive in the growth pattern. There's billions of dollars being thrown at it right now. Consumer electronics, iPhones, GPS, anything that you can think of that's handheld or a small form factor. And then the dark horse that's really interesting is energy storage. California has mandated 2025, all new construction will have solar panels or wind supply to basically supplement the grid. They will need a battery pack to do that, and this is going to be an opportunity that's going to be huge around the world, and we have the material that would be ideal for that. The steps that we're going through, just trying to give you a quick perspective on the journey to commercialization with this technology. We're engaged in the material synthesis step right now. We're very close to a final configuration that will go to the national labs for full benchmarking and evaluation by those partners that I talked about. What we'll be working with in collaboration with them is what's called full cell architecture. So we've totally vetted out the technology. There's no new scientific breakthroughs or acts of God that need to happen. We have a fully functioning anode material that works at those high levels that we were showing earlier. So full cell architecture is melding that with the other components of the battery we talked about, the cathode and the electrolyte and things of that type. Now, one of the things we actually had a preview of a question from one of the participants. How does this fit in with Dr. Goodenough out of University of Texas, Austin? All the announcements, kind of the drumbeat about the next generation of batteries, solid state. Solid state is a reference to replacing the current gel that is in the middle between the positive and the negative electrode, which is called electrolyte, and that's what catches fire, with a solid material. And so that solid material is totally about the transmission between positive and negative, and it does not impact the anode. We would actually be an important additive technology to what he's doing and making it more capable and more powerful. Manufacturing prototyping, the Pyrotech relationship we talked about, they have 38 global manufacturing facilities, one in particular in upstate New York that has capacity that we could do industrial scale manufacturing these materials well within a 1-year time frame from start to finish. Customer partner assessments, this is the sampling that I've talked about, and then there's adoption and ramp up. Just for reference purposes, what we look at is anything going into a car typically is going to be on the low side, 18 months from first introduction, first testing, to 36 to have it in a moving platform. For devices like an iPhone, it's about 24 months. both of these because of the safety issues associated. There's extensive testing. And then things like industrial tools and grid storage and things like that, they can be out in as little as a year, in some cases even less. So we have a rolling introduction to marketplaces that also will impact a rolling introduction of more and more revenues. I mentioned a little bit about our team in terms of the technology team. We've managed to put together a really world-class team. On the left side, our leadership team, as you can see, some of the companies that we've all worked with. This is a team that I could be very, very, very well funded, and I wouldn't be able to find better folks. So we have the capabilities to take this out to international markets immediately, and that's going to be over 50% of the global opportunity for these technologies. On the advisor side, we have a blessing of a number of people that are really at the heart of these technologies. As I mentioned, Brian Holloway had past efforts at Lockheed Martin. He also, while he was at DARPA, funded many of the battery ventures that we've highlighted already, early funding. George Crabtree, Argonne National Labs, and Pacific Northwest National Labs are the two premier energy storage research institutes in the world, and they're two of the 17 Department of Energy labs. So having close association with both of those labs is actually key to our adoption in our future. Also, I might mention at the bottom here, John Waters. You're probably familiar with the fact that electric cars came out in the late 1990s. GM did a very successful test in the Los Angeles area, which what they called EV1. This was built from the ground up, all unique components and unique engineering, and really solving a lot of the problems that Tesla has now done for the mass market. They had a new chairman join in the midst of that trial and had to identify that the Goodwrench business was literally going to go away if they went to the electric platform, because it's so much more efficient, less service, less parts, and that was the cash cow for GM. So at that juncture, they chose to grind those cars up and not enter the marketplace in the late 1990s. It's really set back electric vehicle adoption about 20 years. John Waters was the chief engineer for that effort. So he's really a respected person that understands everything about the electric vehicle from basically cradle to grave in that particular instance, but is really a valuable advisor. We've been recognized on some pretty amazing stages. ExxonMobil last year had 2 weeks of interviews, kind of a bake-off with 137 different companies, and was evaluating a couple that they would like to have present to their executive staff at their annual sustainability day. And it's basically ExxonMobil looking out to what's next as internal combustion engines start to evolve out of the sunset. And we were actually the #1 of those reviewers, and presented to the chief executives of 8 different divisions of ExxonMobil at their headquarters. Future in Review is a conference that's been run for 18 years. It invites Nobel Prize winners, Institute folks, NASA, the head of NASA, Elon Musk. It's that kind of stature. Every year, they identify 6 companies as fire starters, representative of the next generation of technology change. And we were a fire starter this last October. Interesting stat about fire starters: in 18 years of fire starters, over 95% of them continue to be in business and thriving, well past the normals for startup businesses that fail at a very high rate. And then the final is Tech Connect is a international conference run once a year that puts together global industrial partners with core science to try to find basically partners and opportunities to drive new technologies in the marketplace. In 2018, our first introduction and basically coming out of stealth mode, we won the Tech Connect Global Innovation Award as one of the key sciences. And a lot of those NDAs I talked about came out of that event, people that were looking for what's next. So financials obviously is going to be something interesting as you're considering investment. This is the current financial plan that we're working on, which is showing really in the next 2 years, 2020 and 2021, we are in the evaluation stages. We'll be providing samples toward the end of this year to all of the major suppliers, as well as collaboratives with the number of the labs that we mentioned. A nominal amount of investment, something called non-recurring engineering, where people like General Motors would pay us 100,000 or 500,000 or even $1 million to do structured research specific to their needs. So as being a platform, there's several opportunities to do market-specific research sponsored by key vendors, like an Apple and a Google. We continue on with that in 2021, the revenues that we're showing there, and really the first revenues from product sales where we're manufacturing and selling in bulk commodities is 2022. The hockey stick here is pretty amazing. These numbers, these are supported numbers. We've built our business model, whatever, but they are such small penetration into this marketplace. I point out to the fact that the competitors that we talked about earlier, they have been in business now 12 to 13 years. They've raised significant amounts of money, as I'll show in a moment. And they are always kind of on this announcement that we're 1 year away, 1 year away. So we're finding that we actually have the opportunity to potentially be a first mover in this market sector. And the analysts universally have indicated that the next generation of the lithium-ion battery will be with the silicon anode. That is the next breakthrough that gives this technology platform another 15 to 20 years of life as the standard. So we've got a couple of things going on. We have been, we initially self-funded the business for 1.5 years and raised a little over $1 million in a A1 convertible debt round and completed that earlier last year. And then opened up an A2 convertible debt round, which is the current round that has a little bit of headroom available in there, probably up to $1 million, and have a number of folks that are starting to subscribe to that. So I don't expect that to be long term. Our primary purpose in being here today in front of you is that we're opening up our first equity round, and we'll be starting up with that within the next probably 60 to 90 days. Which is essentially the amount of time for due diligence of the early people that have presented for this opportunity. And that will be an equity round where we will finance basically the next level of development, pilot manufacturing, expanding our staff, partnerships with some of the labs we're talking about, and continuing to build the science and patent portfolio. I point out that right now we have just been granted a couple of weeks ago, approved our core patent from 2017, which is a nice protective patent for the process that Dr. Dean was describing. We have 5 international patents associated with that are in process, and 4 additional pending patents on different expansions and extensions of the technology. One is in combination with Washington State University, and 3 additional patents that have been created uniquely by our team that are expanding this platform and its capabilities so that it really can support all those markets we're talking about. This is a particularly hot space. The news, if you've followed it at all, the firm that we've talked about, Sila Nanotech out of Georgia Tech, closed a $130 million round led by Daimler at a $1 billion valuation. So that was kind of cracking the 1 billion valuation. They're the one that for the last 36 months, every time they talk, they say we're about a year out. So that year out becomes the next year, the next year, next year. So in January, their CEO was on Fox News, I believe, and indicated that they were a year or so out and what they expected. They're projecting about half the capability in terms of increased energy that we are. And interestingly enough, their approach is so complex with really expensive precursor materials. We expect when we are market shoulder to shoulder, we're going to have significant cost advantages. But anyway, this is an active space being marketed. The funding that we've raised and how far we've gotten in our progress with the nominal amount we've raised is actually pretty amazing. And we're getting ready to step up to these larger raised numbers. So what are the 5 key takeaways about this technology that you should understand? First of all, this whole notion of swell tolerance. Silicon has been on people's roadmap for a long, long time, but literally, if you put a charge to it and it expands 360%, it will not operate as a battery. It will swell, kind of like the vision of the globe when the continents are expanding. and then it gets smaller and then swells and gets smaller and basically mechanically unstable and breaks apart. And so having a solution that actually solves that, because our cellular structure allows us to swell internally. Visualize washing a car with a sponge, and you take that sponge and put it in the water. It doesn't become any bigger, it just becomes really heavy and dense. And that's exactly the approach that we're taking here, is we're causing our sponge structure to basically build up mass, but not build up volume. Also, the notion here is that graphite is now been invested in. It's, over 99% of the marketplace is a graphite, 100% anode technology. And graphite is, there's a process that goes with that. There's machinery and everything. We are a complete drop-in replacement. So if you just take the graphite out and you drop our solution in, you immediately are looking at a 30 to 50% gain in battery capacity, and also having additional volume, because we're about 1/3 less volume and 1/3 less weight. Thinking of a car, it's a smaller battery and it's a less weight to deal with, but 1/3, 1/3, which allows us to put more cathode in and project greater energy into the battery. There's a tremendous, especially we spent time in Europe earlier this year, a lot of effort being put into green technologies. And certainly our ability to be part of the home storage solution as a fossil fuel replacement. This is one of the key things that allows us to compete for government sector opportunities, and for certainly for a different type of investment strategy. Some of you are probably in family offices that have a green agenda. We'd certainly like to talk to you about how we fit in. Talked about the patents already. The team that we have is pretty amazing. There's 7 PhDs, 4 attorneys, and 7 ex-CEOs involved in the team. So we have great leadership. There are no key hires that we have to make. We just hired a new CFO on February 1st. That was at Ernst & Young, spent 13 years at Starbucks and 11 years running the innovation fund as CFO for Bill Gates Intellectual Ventures. Really a top-class guy and helping us tremendously. So that's the core of our presentation. We have done financial models, and I just want to run through these briefly so that if it's of something of interest to you, we can actually go into greater detail later. The pro forma income statements reflected in the chart earlier is that we're essentially not into a position of being profitable until after 2022. But the hockey stick that's involved there, if you think about it, when you have a market opportunity, as I presented earlier, of $100 billion in 2024 for lithium-ion batteries, with about $15 billion of that associated with the anode materials. So projecting $144 million in sales in 2024 against a $15 billion addressable market, I think we're being very, very conservative. So I don't see this, I've been around this long enough to know everybody says they've got a hockey stick. I believe the pull for this technology, the need to have higher capacity, higher mileage capacity for cars, devices. I've got a new Apple iWatch 5, 18 hours. I can't even wear it multiple days. Your phone is dead and recharging in the afternoon. All of these types of annoyances that keep us from really being even more dependent are addressed by this technology. Second, in terms of balance sheet, this is reflecting some of what we were talking about in terms of our investment flow. We've done basically nominal capital stocks so far. We have about 6.7 million shares outstanding and about 800,000 shares combined of options and warrants. So overall, about 7.5 million shares is the float at this point. Cash flow statements, this is really reflecting the chart that we talked about earlier. So at this juncture, we're about 35 minutes to this. I know we've got an hour. I'd love to address any questions and any kind of clarifications. This is a unique situation in the sense that I think it's important to understand batteries, to understand the consequence of what we're doing. I think it's pretty obvious to people that more battery capacity is going to impact a lot of industries in a very positive manner. And if you've got the best horse in town, obviously people are going to buy in mass. But sometimes it's difficult. We kind of get lost in the weeds trying to explain what this is. So feel free to engage us individually or in your questions here if you need further expansive, why an anode's important or things of that type. But I'll address questions at this point. Thanks, Lindsay.
Thank you, Jeff and Jerry. We do have some fantastic questions in the queue already, so I will let Jeff take those from here. But again, I do want to encourage everyone to use their chat option and send over additional questions at this time.
Great. Jerry, the first question I think that I see here is how many charge-discharge cycles have been demonstrated in a fuel cell, in a full cell?
Okay, go ahead, Jeff.
Oh, sure. Okay. Well, at this point in time, Ecellix is about 6 months into running our own laboratory after exiting the university. And so we are developing half-cell technology at the moment and continuing to advance the physics of the material itself. We expect that we'll be in full cell development here within the next 2 to 3 months, working with some of the partners you saw on those slides before. Some of the reason why we think that is we're further along than that might reflect is that the material performance that we're seeing at the half cell has a number of characteristics which are often solved at the full cell. And so we're solving those problems earlier in the material itself. I think that's probably as far as I would go at this point in time. So Jerry, let's see what else we can answer. Energy density roadmap for kilowatt hours per kilogram. I would look at this, the numbers that are out there today for kilowatt hours per kilogram are all over the map. You'll find numbers from 100 to 265, 270 kilowatt hours per kilogram, based on who we're talking about, whether we're talking about an individual cell or a battery pack in a vehicle. What we're talking about is whatever those numbers are, they're all based on a graphite anode, a carbon-based anode. And when we change that to a silicon-based anode, we increase that by about 30 to 50%. 30% on the conservative end, 50% on the aggressive end, using all else being equal. So whatever we're able to achieve with cathodes and electrolytes in other technology, we believe we'll be able to boost that by 30 to 50%. Just on a rough scale, we look at the 7100 batteries that are in a Tesla Model S. And when you go to a silicon anode, the number of battery cells drops down towards 5,000. That's the kind of impact that you have overall when you start moving to a more energy dense anode. I'm seeing questions coming in quickly. Let me scroll back up and make sure we're covering these in order. We had a question about how many let's see, what role Cabot plays. At this point in time, I wouldn't talk directly about the roles that our partners play in our technology development. It would get a little bit into the intellectual property that we're creating. Cabot's specialty is in working with graphites, with carbons. And so in any battery, you've got a combination of carbon and silicon in order to make your battery. And I'd sort of leave it as that. Cabot and Croda both work in applications of carbon within the battery. Projected added cost for the 30% capacity. This is a really interesting question overall. We believe we'll be able to make anodes using our material at the same cost or maybe even a lower cost than what we're making graphite anodes for today, meaning the overall cost of the battery should stay flat or maybe even get a little bit better. There's a catch to it, which is that in order to make the battery using a silicon anode, we're using about 1/5 to 1/3 of the mass of powder to make that electrode, to make that anode. And so the cost of our material can be higher on a cost per weight because we get to use so much less of it. That's a really exciting and interesting advance. That's baked into the analysis of 30 to 50% increase on the battery. So we think what we'll be doing is we'll be increasing the capacity of a battery cell, and we'll be keeping the cost of that battery cell at least flat, if not improving it. The fraction of the cost in the anode. Jerry, would you want to talk about that a little bit?
Yeah, it's actually an interesting opportunity for us. The calculated cost of the anode subsystem is 25%. And what that would mean is taking our material with a binder, with a foil, and creating an anode. And that's actually something that we could possibly do. It actually sells in sheets, and so it would take us up market and create a new revenue opportunity. If you were just down to the active material where we were selling to Samsung, for example, to make their batteries, it's about 15% of the overall cost. So that's that associated 25% for overall anodes, which we could certainly do. It's within our wheelhouse. We have expertise and IP in that, or alternatively, a more simplistic model and a cheaper capital model would be just to create material and sell the material.
I see a question down below. I'm skipping over about sharing materials on the, but about solid state batteries, a little bit more on solid state batteries. So solid state batteries are principally exchanging the electrolyte. So as I said before, we're moving ions between a cathode and an anode, moving them as I charge them. The ions move from the cathode to the anode. They move through the electrolyte. And then as I discharge, I move from the anode to the cathode, moving through the electrolyte. So the electrolyte is a carrier or a transmission medium for those ions. Right now we're using liquid, and that liquid has a number of problems with it. It's long-term unstable. It tends to be flammable. It has a number of challenges. It's reactive. So it has a number of challenges in terms of how you make a battery that are limiting. And so people have been looking at building solid state batteries for quite a while. And there's a lot of research going into that area as well. And that is, how do I replace the electrolyte with a solid gel or a different kind of a matrix? So earlier today, we had a question that came through regarding John Goodenough, who was the founder or sort of the original godfather of lithium ion batteries. His group is working on a technology using a sodium glass electrolyte. And again, they first announced that work in about 2017. It's continuing to evolve. We watched that. It's very, very interesting. There are a number of groups who are working on solid state electrolyte, from BMW, Dyson, Honda, Hyundai, Nissan, NGK, Volkswagen, Mercedes-Benz. All of these companies are investing in solid state electrolyte. To date, when you go to the technology conferences, people still talk about that as something that is quite a ways off. It's still in development. It's something that's very interesting and we're watching closely, but I think that is going to be a subsequent wave of technology, not the next wave.
And that's actually raises an interesting point. I was a participant in the major European battery conference back in January actually. And for the first time, there was a general acknowledgement that the next step in evolution of the lithium-ion battery was this incorporation of silicon anodes, that the technology had finally matured enough that they were looking in the roadmap that was going to be the thing that was going to yield this 30 to 50% gain, and was going to make that the platform of choice for the next 15 years. And then we're looking at probably in the 2030 range is the predictability right now in terms of solid state. And so one of the things we've looked at long is, well, what happens? Do we become redundant and not viable as a company at that point? And what we've found through a lot of different engagements is that actually we take what they're trying to do and make it more powerful because we empower the anode. We still end up being the big dog on the block. I was going to show you too, this is a battery. It's called an 18650. This is what's in a Tesla. A P100, I think, has like 8,100 of these. They're a little bit bigger than a AA battery, weigh an awful lot more, like 10 times more. So it becomes really the weight factor in a car. The heavier the weight of the battery, the more power you have to have, the more impact on balancing the ride. So if we can take that weight down and take the number of these cells down a third, that's a major improvement. I think I saw at one point it was the metric for the automobile industry was every pound saved was worth $300 to them in their metrics in terms of costing model. So we can save quite a bit actually.
Jerry, you want to talk about burn rate?
Yep.
Question I see here on the list.
Yeah, so I showed that extensive team, and I think if you look at that, you go dollar signs, dollar signs. The reality is that all of my senior management are operating somewhere in the 30 to 40% of their market rate. They're heavily equity incentivized. We believe in this technology. As you see the pedigree of the folks, we all have opportunities to do a lot of different things, and we choose to devote ourselves to this. Our burn rate before kind of COVID hit, we're up about 103 a month, and going along quite nicely. And we're now down to, well, our fixed costs are 82,000 a month. We've got some variable on top of that, but we're definitely under $100,000. So the raise that we're doing right now takes us comfortably at this rate well past the beginning of the year. And if what I'm really looking to do is I'm looking to light up a lot of those partnerships. We can expand our lab only so much in terms of finding the right candidate, get them ingrained, get the laboratory set up, expanded to support that. But there's large labs like Polaris that we talked about that have hundreds of employees. They have the functional equivalent of our lab setup, maybe times 100. And by contract, we can set that loose. The thing to understand is that this is not like a traditional product development or a tech hardware product or software. This development is much more like biotech. And so you have a number of investments to get yourself up to a state that you can do trials or you can get FDA approval or whatever. We're in the same type of situation. So there's front-loaded investment, but once you get yourself to that state, everything happens pretty rapidly. So when we talk about the national labs, we talk about partners, we're all about getting this to a point that somebody like a GM can make a positive decision and say, absolutely, this takes us from a 250 mile range volt to a 400 or a 500 mile range volt, which changes our competitive capacity, especially if it controls the cost. So we're very much in the costing structure and the architecture, weight distribution, size, all those types of things. We really have a disruptive influence on the automobile industry and make EVs a lot more viable.
So I'm going to try to group a series of questions as we're down to our final 10 minutes here. There's a number of questions around risks associated with the technology, where we are in terms of the development state, what we need to be accomplishing in the near term, even a question there on temperature performance. So let me try to address those all in one group answer here. The state of the technology right now is in material science of the anode, which means when we start off with a better material, we're actually able to solve problems before we actually have to solve them at the full cell. So we are building materials that have the right properties in terms of conductivity, in terms of swell tolerance, in terms of stability, in terms of chemical reactions. And that's what we've been working on both at Washington State University and in our laboratory at University of Washington. So at this moment in time, we have taken the concept of advancing the material science of our anode material quite far. And we're about ready to move to a place where we're looking at this at a full cell. So on the scope of some of the other battery companies that have been around since 2008, they of course have gone to a place where they've been trying to solve a whole litany of other technology problems that were introduced because of the structure that they're using. In our end, we are optimistic that as we move forward, and that's optimism is based on feedback from other groups, including national laboratories and some of the partnerships you see there, that as we move forward, we're going to be moving into full cell chemistry with a lot more success. I'm looking at some of these other questions to just make sure I have here. So questions about final prototypes and how far we are. At this moment in time, we're not making full cell batteries. It's not the primary challenge of the company, and it's not where we're demonstrating our uniqueness. Where we're demonstrating the uniqueness is in the material that we're producing and how it performs relative to other material at this scale. We've put together a consortium of partners who are going to really help us accelerate and speed that time to market. And we know what we can bring to bear with our technology. So we're starting off with an anode material. And as you go to combine that with cathode materials and combine that with electrolytes, there's a much better understanding of how to do that today than there was 5 years ago or 7 years ago when many of these other technologies were first getting started. And so we really believe that we're in a much better footing for launching into that next step. We've done some experiments looking at temperature dependency of the anode material. Thus far, we don't see anything with the material itself that would cause us any concerns. See a high ability to perform well over a range of temperatures. As we combine that with electrolytes and cathodes, we may see changes in that, but I think that's something that we're going to have to address as we move into that next phase. As we go look at the IP portfolio, there's a question there about the IP landscape. We keep dossiers on every company in the industry, looking at the intellectual property that they filed, any scientific literature that they have published, all of their public relations material to try to understand what they're doing and how they're approaching it. And we've made a study of that, and we've also gone off and talked to experts who've worked with and been around these other companies for quite a long time. Every one of those companies is different. And it's hard to make generalizations about them without talking about each one of them specifically. Let me try to make some generalizations anyway as a whole. Almost all of those companies are trying to solve the problem of silicon cracking by starting with small particles and then solve the problem of these surface chemical reactions by building complex structures from the bottom up. When they do that, they're starting off with materials that are hard to handle and expensive, and what they end up with are structures that are somewhat inflexible and hard to change, hard to modify or tune, so that when you go to combine those materials with the other parts of the battery, the cathode, the electrolyte, the binders, other parts that make a battery, their material doesn't have a whole lot of room to give. They're asking for, they have to develop all these ancillary technologies to work with their limited flexible material. When we work with a material such as ours, which we have a lot of tunability on, we have a lot of flexibility in how we make it, it starts off being very cost competitive and easy to handle, simple to synthesize. When we start off from a much better physical properties of the material, we're actually able to drive to a place where we think we're going to be able to combine other technologies with ours, the electrolyte, the separators, the cathodes, in a faster, more advantageous way. So our intellectual property is distinguished from everyone else's intellectual property around that concept, that we are starting off with a top-down synthesis, looking at this porous silicon carbon composite that has the physical properties that if I was setting out and saying, what should an electrode material look like? What should an anode material look like to behave optimally? I would draw a picture of a porous silicon carbon composite. And that's what these other literature, these other authors are saying now, is after having looked at this whole suite of technologies that have developed over the last 20 years, they're now looking at this, and the research that's ongoing at the national laboratories is on porous silicon carbon composites. That people are moving in the direction of trying to find ways of making these. So our research team was clever, and we're able to see this coming a little early. And we created a very novel synthesis method that was both easy, scalable, and inexpensive. That's what we filed patents on, and that's what we're continuing to protect. I'm seeing new questions, Rob. Jerry, do you see any that have come up?
Two other things I'd interject there. We've referenced many times University of Washington. Actually, a bit of a misnomer. We are one of 6 resident companies at the Washington Clean Energy Institute, which is a funded state-of-the-art clean energy research lab, and it is operated by the University of Washington. It's just off the University of Washington campus, but this is a facility that probably saved us $2 to $3 million of capital investment in probably at least a year, because it was turnkey for us. We walked in with a few equipment supplements that we purchased. We had everything we needed to do to drive this technology all the way to success. The other thing I wanted to mention is this difference between bottoms up and top down. The materials, when we start at that large scale and at commodities, just off the street type quality, it's very inexpensive. When you flip around and you're looking for nanotubes, nanowires, graphene, all of these different types of exotics, the numbers that we find is anywhere from 10 to 100 times more expensive per quantity, the materials that they start with to build their structure than we do. So there's some really baked in economics here that show at the end when we all get to marketplace, and hopefully we're the first, that we have an opportunity to have a really significant cost advantage.
There are some questions that are in here. I can answer quickly. The battery sizes maintained, increase in capacity is 30 to 50%.
Across any file format, so any size battery. It's not these little ones. It can be the phones, it can be the house. We're agnostic in terms of use and platform.
So in an 18650 cell, the same size and the same weight of battery, we would be increasing the energy capacity by 30 to 50%. Yep. Liquid electrolytes, how do you become intimate with the surface, anode surface? And then there's another follow-on question about dendrite formation. These are both questions that we could spend the large part of the day talking about. And so what I would suggest is, if you're interested in hearing more, let's set up a time further on, and I'd be happy to talk to you in more detail about it. Real quickly on dendrite formation, we're looking at the electrochemical potentials of our material, and because of that, we don't believe we have a dendrite formation problem. In fact, we think that our material will be operating in a place with much less of a dendrite. Dendrites are hair-like structures which can cause shorting of a battery or contact between the anode and the cathode. And we don't think that those are going to be formed as readily on a stable SEI layer, solid electrolyte interphase layer. That's those surface chemical reactions I was talking about. And questions regarding the solid interphase with a solid state electrolyte, that's a deeper question that perhaps we'll take offline. Jerry, you want to talk about the deal terms on the previous convertible notes?
Yes, so the note one, the biggest significant difference was that it was the first funds that we raised. We were just pulling this out of the university lab, and we agreed initially, brought in some money with no cap, and I had a couple of larger scale investors that wanted to participate, but absolutely would not do it without some kind of a cap on valuation. They didn't want to bankroll us into great success and then be penalized by that. So we did a $6 million cap on the original raise. In note two, the one that we're completing right now, we increased that cap to 12 million. But it's essentially the norm is kind of 15 to 25% discount or a $12 million cap for conversion, one of the two. And the trigger event for conversion is the first million of priced equity raised will be the index for how it converts and the covenants and terms and classes of stock that it converts to. So it'll convert to like of whatever the first million is.
Perfect. And Jerry, I hate to cut you off, but we do only have a few seconds left on this webinar. So on behalf of Family Office Networks, I wanted to thank everyone for attending, Jerry and Jeff from Ecellix. We will be following up with everyone individually as well for any further questions. We hope you have a great day.
Excellent. Thank you very much, everybody.
Thank you all.
Have a great day. Thank you.